space. And let's take disjoint subsets, pairwise disjoint subsets. I'm going to call them I, J, and K of the index set bracket n. So bracket n is just 1, 2, up to n, the first positive n positive integers. And for that choice of triple, we consider the so-called conditional independence statement. Conditional independence statement, and the notation is I is independent J given K. Okay? So this is a statement that we can make about a distribution. So a distribution either satisfies this statement or it doesn't. Okay? So independence you know, but this is conditional independence. So maybe, your income is independent of whether you're good at hiking given your ethnic background. Maybe that's a true statement. This may or may not hold about the world. Okay? So formal definition. So this statement holds for a joint distribution so if you have a joint distribution P, then what you want is that for any assignments of states A, B, and C, the probability of xi being A and the probability of xj being B, given that xk is C, that should factor as the product of the probability of xi being A given xk being C times the probability of xj being B given xk being C. Okay? So xi equals A means the following. I is a set, a subset of the variables. So maybe the first variable, the fourth variable, and the eighth variable. And this means we're assigning states to the first variable, the fourth variable, and the eighth variable, and we're summing out over all other states. Okay? And conditional independence, this is given by fractions, right? We'll give you an example in a moment. Now, this definition works essentially also in the continuous case. So if the distributions are continuous, as they will be at 1130, if the distributions are continuous, we cannot talk about distributions, but we only talk about densities. Okay? So then use, in the continuous case, use densities. Okay? Right, so in a continuous distribution, the probability of every single event is 0. But then, you have a range, right? Then you integrate, and then so for continuous case, this same equation holds, but for the density function rather than for the probability. Now, independence is a special case of conditional independence when K is the empty set, right? So something is independent of something else given nothing. Well, that's just independence. Familiar notion of independence. So let's go over the discrete case first. So in the discrete case, for example, let's look at binary random variables. Let's look at 4 binary random variables. And let's take I to be the singleton 1, J to be the singleton 2, and K to be the singleton 3, right? The set of all distributions that satisfy this statement is a model. That model is a subset of the 15-dimensional simplex. 2 times 2 times 2 times 2 minus 1 is 15, right? So if we have 4 variables, binary, we're in a 15-dimensional simplex, and we have specified a model. What question maybe should we ask about that model? For example, the dimension. Exactly. First question, how many degrees of freedom does this conditional independent statement have? 1 independent of 2 given 3. Right? So let's derive this. So a joint distribution is a table. Pijkl is a 2 by 2 by 2 by 2 table. And then the statement down here translates for all A, B, and C. Now there are states between 0 and 1. So for all choices A, B, and C that are 0 or 1, we have P A, B, C plus divided by P plus plus C plus is equal to P A plus C plus divided by P plus plus C plus times P plus B C plus over P plus plus C plus. Okay? That's the translation of these conditional probabilities. So the conditional probability that the first variable is in state little a and the second variable is in state little b, given that the third variable is in state little c, is this fraction. And we're summing out the fourth variable. We're not making any statement about Martians and so on, right? So that's this ratio, provided this number is not 0. Okay, so always when you deal with conditional probabilities, you have to be a little bit careful, what 0 divided by 0 means, but that's the definition of conditional independence. Okay. Now, this is the statement: 1 is independent of 2. Given 3. So these equations, these 8 equations, cut out a set in the 15-dimensional simplex whose dimension we are dying to know. Okay? Now, to deal with these equations a little bit more nicely, we clear denominators. You can clear denominators and rewrite. And you get the following. The determinant of this 2 by 2 matrix, P0, 0, 0 plus, P0, 1, 0 plus, P1, 0, 0 plus, P1, 1, 0 plus is 0. And we're conditioning on the third variable. So here the third variable is in state 0. Right? Now here we're doing exactly the same thing, we're just putting it in state 1. P0, 0, 1 plus P0, 1, 1 plus, let's do them all American, after all it's 4th of July, P1, 0, 1 plus, P1, 1, 1 plus. Okay, so that is equal to 0. So those are the two equations. And so this thing is codimension 2. It's a 13-dimensional set inside the 15-dimensional simplex. So if you clear denominators and regroup, you get this statement. This probability times that probability is equal to this probability times that probability. That's a conditional independence statement. If you look at the structure, we're summing out the fourth variable. We're making no reference to it. We're fixing the third variable. We're fixing whatever is after the bar. We're fixing that state. And then in the first two, we do the familiar Markov 2 by 2 minors that we've seen many times. This works for any collection of conditional independence statements. So in proposition 8.1 of the notes we've been using all semester long, we find the following. So this is the polynomial system solving book, proposition 8.1. The statement that I is independent of j given k translates into a system of quadrics, of quadratic homogeneous quadrics. These are 2 by 2 minors of certain flattenings. Okay, so we have this 4-dimensional tensor. We're summing out the last state. We are taking a slice in the third state, and then we're taking a 2 by 2 minor. Okay? This always works. So whenever you see a system of conditional independence statements, gender is independent of income, given weight, and marital status. Smoking is independent of cancer, given the planet you were born. Blah, blah, blah. You might have a number of these kind of statements. In the discrete case, they translate into a system of homogeneous quadratic equations that you can write as 2 by 2 minors. Algebraic geometers love projective varieties defined by quadratic equations, and we're giving them some. Whenever you have a system of conditional independence statements and you fix lowercase ABC, you have a projective variety. Now, flattenings in marginal probabilities. Now, a special case, if I union J union K is everything. So here I assumed that I and J and K are pairwise disjoint if their union is the whole set. Then something nice happens. Then there are no pluses anywhere. Then you don't see any pluses. Then we get quadratic binomials. We get quadratic binomials in the probabilities. So in the literature on these kind of models, this is called a saturated statement. So if this holds, we're going to call that a saturated conditional independence statement. Okay? So here in this case, 1 is independent of 2 given 3 is not a saturated statement, but 1 is independent of 2 given 3 and 4 would be a saturated statement. Okay? So this translates into honest quadratic binomials. And this requires a little practice. It's not hard, but it just requires a little practice. So you make a list of these statements, then you have to sort of write down, these matrices, and then you get quadrics. And I think there's a Macaulay 2 package, right? Where you just draw the graph and it makes this ideal for you. But it's good to practice on a small example. So then in general, by a conditional independence model, we will mean a list of conditional independent statements. Okay, so if you make a list of some statements, I independent J given K, and some other thing, whatever is defined by that is a conditional independence model. So that's an equational description of a statistical model, which unlike the wiki is not given to us in parametric form. It may or may not also have a nice parametric form. Okay? Now, if all statements are saturated, that's a particular nice situation. If all statements are saturated and we are in the discrete case, because it's not 11:30 yet, we're in the discrete case, then the model is toric. And the model is toric. It's an exponential family. It's a log linear model, so it has a Markov basis. All right, so a toric variety is one that's cut out by monomial minus monomial, by binomials. And if we have a list of saturated conditional independence statements, on some space of tensors. We have a list of quadratic binomials, and that cuts out, interpreted appropriately, such a model, and it has a Markov basis. Now here's a question. Which conditional independence models should we study? And we want to make statements about the world, right? The world has n random variables, right? And we want to make some statements and want to reason about the world. We ideally would like to do some causal inference. The subject studied by Robin Evans, fantastic speaker, Thursday in a week. Which are models, well, they have to have some good interpretation, right? If I write down some crazy list of conditional independence statement, maybe that's interesting mathematically, but I want to sort of understand what's going on in the world. And the ones that are favored by everybody are so-called those arising from graphs. So somehow graphs is a structure that people can understand, right? If there's a graphical structure on our random variables, then we can make sense, right? So there's a link between this gene and that gene, we put an edge between it. Or maybe directed edge, right? This gene regulates some other gene. Or something causes something, right? Maybe smoking causes cancer, perhaps. Okay? So a graphical structure is one that we like. Now, there are today, and mostly in this discussion, there are undirected graphs and there are directed graphs. Now it turns out in the literature on graphical models there are tons of graphs. There are bidirected graphs, there's all kinds of directed graphs, I don't quite know about multiple edges, but people have come up, chain graphs, people come up with all kinds of decorations on the graphs. But today we'll just do the plain vanilla version. We either have a simple undirected graph or a simple directed graph, which also will be acyclic. Now another source, I mentioned this already, is these Oberwolfach lectures in algebraic statistics with Matthias Sturton and Seth Sullivan. And so this material is in section 3.2. Okay, so conditional independence statement is a list of statements I independent of j given k, where I, j, k are pairwise disjoint subsets of the set 1, 2, 3 up to n. In the discrete case, this translates into a whole bunch of quadrics whose variety you can study if you're so inclined. Okay? Now what about these graphs? So let me describe these two flavors of graphical modes. So here's the undirected case. An undirected graph, and the set of nodes or vertices is 1 up to n. So bracket n is the set of nodes in the graph. And these are also known as Markov random fields. So these are known under different names. So if you're coming more from the physics side, they're sometimes called Markov random fields or Ising models, depending if the graph looks like a grid. Then people call this an Ising model. So here we'll just call them undirected graphs. I'm given an undirected simple graph, simple, on nodes 1 up to n. Markov random field. Well, in the discrete case, these are going to be toric. Okay? So I'm going to read off a list of saturated conditional independence statement from any graph. Maybe gives me a graph. I'm going to read off a list of saturated statements. Each saturated statement gives binomials. So I've got a toric variety. Okay? The log linear model. And the statements that we read off from a graph, they're like this. So the conditional independence statements, the most basic version is you take a singleton I and a singleton j, and these two singletons are independent, conditioned on everybody else. So I is independent of j given the entire complement, and you require this for all non-edges. So whenever you see a non-edge in the graph, so if I and j are not connected by an edge, you write the statement, the singleton I is independent from the singleton j given all the other random variables. That's a saturated statement, right? Because this union that is everything. So by the algorithm that I explained much too quickly, but which you will practice this afternoon, this translates into a long list of quadratic binomials in the P's. Okay? So for example, this afternoon we're going to look a little bit at this graph. So this is the 4-chain graph. So n is 4. So when I say study the 4-chain, study the 4-cycle, I mean this, the 4-cycle graph. So to write down the conditional independence statements, you make a list of the non-edges, and then each non-edge translates into a conditional independence statement. So this graph has two non-edges. 1 and 3 is a non-edge, and 2 and 4 is a non-edge. So the non-edge 1, 3 translates into the statement 1 is independent of 3 given 2 and 4, and then the second one is 2 is independent of 4 given 1 and 3. So by this I mean the singleton 2 is independent of the singleton 4 given the set consisting of the elements 1 and 3. Okay? So that's an undirected graphical model. Let's do the directed case. Okay. So every undirected graph on n vertices on some space of n-fold tensors gives you toric variety. That toric variety has a polytope and everything that comes with the toric variety. Okay? A Markov basis. Okay? Now in the directed case, it's a little different. So let's look at directed graphs, and let's make them acyclic. Okay? Just for simplicity, let's look at directed acyclic graphs. There's also versions, without the acyclicity. So these are called DAGs. Okay? So a DAG is a directed acyclic graph. Again, there are many words. Sometimes these things are called Bayesian networks, and so on. Okay? Now these are usually not toric. Most of these models will not be toric. They will not be toric because they will not be cut out by binomials, because the conditional independence statements I'm about to write down are usually not saturated. So therefore these things will not have a Markov basis. So the question asking for a Markov basis in this case is a meaningless question. Okay? So here the conditional independence statements are as follows. You write them down and I'm going to explain. They look like this. I, a singleton, is independent of the set ND of I minus PA of I given PA of I, okay, for all nodes. I'll explain what these sets are for all nodes I. So ND, or PA, is the set of parents. And ND is the set of non-descendants. Okay? So you're in a directed graph, an acyclic directed graph, right? So, you know, you have a grandmother has an arrow to father, has an arrow to child, right? So you think about this. So in a directed graph, an acyclic directed graph, every person has parents. Those are the, you know, so my parents are those other nodes that have an edge from them to me. So if I'm node I, PA of I, the set of parents of node I, the set of all nodes that J such that J to I is a directed edge. So the parents. Okay? Well, a descendant is everybody downstream, right? So some other node K is a descendant if it's your child or your grandchild or something, right? So if there's a sequence of directed edges from I to somewhere to somewhere to somewhere to K, that's a descendant. Well, a non-descendant is somebody who's not a descendant, right? So everybody who's not a descendant is a non-descendant other than you. Now your parents are non-descendant, but those are sort of trivially non-descendants. So you take them out. So ND of I is the set of non-descendants of I other than yourself and your parents. So for example, your grandparents are in this set. And your cousins usually in this set. Okay? So for example, okay, let's do this graph. Let's do again the 4 cycle. Okay? But now I'm going to make it directed. So acyclic directed version, and this is 1, 2, let's call this 3 and 4. So just to have the same incidence structure. Okay, so now there's one possible statement for each node. Okay, so let's look at node 1, for example. Then 2 or 4 actually give the same statement, and 3 gives a statement. And then these things give rise to independent statements. Okay? Well, let's look at 1. So 1 doesn't have any non-descendants in this example. Everybody is a descendant of 1, so there's no statement. Okay? Because I and J should be non-empty sets. I should have said that. I, J, and K. I and J should be non-empty, and K could be empty. But, you know, so there's no statement. But 2 and 4 actually give the same statement. So look at 2. Okay? So 2 is independent of its non-descendants. Well, the non-descendants are 1 and 4, but 1 is a parent. So we take them out, right? So if I is 2, this set is 4. So you get 2 is independent of 4 given 1. Well, that's a statement. So 2 is independent of 4 and given 1. And then we get 4 is independent of 2 given 1, but this commutes. So independence, you know, commutes, and so 2 is independent of 4 is the same as 4 is dependent of 2. So both this guy and that guy give this independent statement. So what about 3? Well, 3, everybody is a non-descendant, but the parents don't count, so only the grandparents count. Okay, so 3 is independent from 1, from his grandparents, given the parents, the 2 and 4. Okay. So in this directed graph, in this DAG, in this Bayesian network, we get 1 non-saturated statement and 1 saturated statement. Now, direction of edges, I mean, there's a big question, you know. We put, you know, causality and Robin Evans. So I think that's one interesting direction in algebraic statistics, is how can you use algebraic geometry to go from a correlation structure to a causation, right? We don't want to just say that smoking and lung cancer are dependent or correlated. We would like to say one causes the other, right? There should be a directed edge between these two random variables. So how do you quantify that algebraically? Very interesting topic, one of many, many interesting topics to be discussed at the workshop.
What do you mean the acyclic? What do you mean?
Oh, acyclic. So acyclic, I mean there's no directed cycle. So directed graph. So this has a cycle, but it's not a directed cycle. Yeah? So a directed cycle goes I to j to k to l, you know. So very good question. So acyclic means no directed cycle. Any other questions? We have 48 seconds for questions, and then we get to continuous models. Again, so this is not difficult, but it requires a little practice. Okay, the normal distribution. Gaussian models. Okay, so now the state space is not discrete, but it's R to the n. Okay, so well, usually in your first course in statistics, you see a picture that looks like this. Right? So you take, you know, even high school, right? If you ever take statistics, then you see this picture. Okay? So what is this picture? This is the real line, R1, and you have, this is the density function of some distribution on the real line. Okay? Now, there's two parameters in this model. Mu is the mean. That tells you where this curve peaks. And then there's the covariance, sigma, that tells you how wide the curve is. Okay? So this is the density function. This is a function whose integral, the area under the curve, is 1. Okay? So you calculate the area under the curve, it's 1. And that gives you a continuous distribution. The probability of every single event is 0, right? The probability of meeting somebody who is 1 meters and 97 centimeters and blah, blah, blah is 0. You're never going to meet that person. But to meet somebody in this room, you know, between 192 and 198 has a positive probability, okay, in this model. That's the integral of the density from 192 to 198. Okay? And mu is the mean height of the population. Okay? So we're doing this in n-dimensional space. So Gaussian models are parametrized by pairs mu sigma, where mu is the mean. That's a vector in Rn. Now this is Rn. Down here we have Rn. And then sigma is a positive definite n by n matrix. So PD of n is the open n plus 1 choose 2-dimensional convex basic semi-algebraic cone of positive definite symmetric real n by n matrices. Okay? That's the open cone of positive definite real symmetric n by n matrices, and that's the covariance matrix. So the role of the covariance that tells us, you know, the shape of this bell curve is now played by a positive definite quadratic form denoted sigma. So this is the mean, and this is the covariance matrix. Okay, the positive definite symmetric matrix. This is theta. This is the parameter space theta for all Gaussian models. So in the wiki definition of statistical model, this is a statistical model, right? It's a family of probability distribution parameterized by some parameter space capital theta, namely this product space. Let me tell you the density. You don't have to look at it again, but I think one should see it at least once, right? So there's 1 over 2 pi to the power n over 2, determinant of sigma, the square root thereof, and then times the exponential function, a half x minus mu transpose, that's a row vector, sigma, that's a square matrix, x minus mu, that's a column vector, and that's a number. Okay? So again, sigma is the positive definite quadratic form. I'm multiplying by x minus mu. That's a vector. That's a non-negative number, right? Minus half times that. That's a non-positive number, okay? Then you take an exponential of a non-positive number. That's a small positive real number. And then you normalize by this thing so that the integral is 1, the area. No, I think this is okay.
No, there.
Or sigma inverse here?
Because in the one-dimensional case, it's 1.
Okay, maybe I have sigma inverse here. Okay, please double check. I might have a typo. Okay. So Alina knows this better than me, so I trust her, not me. Yes, Spencer.
Is the intuition behind why this is a positive definite matrix is that we're choosing standard deviation in each direction, and we do a change of coordinates somehow, which
yeah, so
diagonalizing, and that gives us the
exactly. This gives us sort of the principal directions. Okay. Okay. So this thing is some function that integrates to 1. Okay. And you don't want to look at it ever again, right? Because we're algebraists. At least for a little while, we don't want to look at it. Okay. So we're going to just work in the parameter space. Now let's do this. Typically what we do is we ignore the mean. We sort of place no constraints on the mean. We sort of don't care really what the mean is. What we care mostly is this positive definite matrix. So every subset theta inside the positive definite cone. Every set theta defines a model. And we leave, mu unconstrained. Okay? So if Rainer has a favorite subset of the positive definite n by n matrices, if he likes some subset, that's fine, right? So his subset specifies a Gaussian model. Namely, all the distributions where sigma is in his subset. Okay, that's what I mean by a Gaussian model. Now, what about the data? Okay, let's talk about the data. Statistics is the science of data, analyzing data. Big data, of course, are popular. I like small data, but any kind of data. So let's take samples from such an unknown distribution. Let's call them x1, x2, up to xn. These are vectors in R to the n. So these are now numerical measurements, right? So earlier we had categorical variables, right? Where you like beer or you don't, right? Now we have numerical measurements, okay? So we measure n things about Jose, right? How tall he is and how much beer he drinks or whatever, right? There's a bunch of numbers, okay? So for Jose, we have a vector of real numbers, and for every person in this room, we have a vector of real numbers. We measure n things, okay? And we have how many people? Let's say we have p people in this room. For each of the p people, we measure n things. Then we can do the following. We calculate the sample mean. And the sample mean is just the average. So it's 1 over p, I from 1 up to p, x upper I. Right? So we average these vectors over all p people in this room. Right? So the average height and the average beer consumption and so on. Okay? There's also the sample covariance matrix. And that's the following. That's S. So that's the average of a bunch of rank 1 matrices. I from 1 up to 1 to p of xi minus x bar transpose, that's a row vector, times the corresponding column vector. xi minus x bar. Okay? So what is this? So we first of all, x bar is the mean of the sample. We're averaging the measurements for everybody in this room. Then xi minus x bar is how you deviate from the mean. So if I is, one of you guys, right, then xi minus x, that's a vector of positive and negative numbers that tells you how you differ from the mean. Then you form the corresponding rank 1 matrix. Right? That's this row vector times that same column vector. That's a rank 1 n by n matrix, and then you average them up. Okay? This average is a positive semi-definite matrix. So this sample covariance matrix may lie in the boundary. Okay, and exercise 9 and 8 is all about that. People are very interested in this. So if you have maybe every sample, is expensive, right? You can't measure this for everybody in the room because it costs you a lot of money, right? You can only maybe sample for 4 people in this room. But n is 10, right? Then you're going to be in the boundary. So if you have few, but if you can sample everybody in Dijon, then you're going to be with highest probability in the interior, right? So if you have few samples, then you're going to be in the boundary. If you have lots of samples, you're going to be in the interior with your sample covariance matrix. These things play the role of the row sums and the column sums. So earlier we talked about the sufficient statistics, right? So we said, we do these Markov chains, we're fixing the sufficient statistics. These are now the quantities that play the analogous role. Okay? Now, here's a proposition. Now, in this setting, you can do frequentist statistics, you can formulate and maximize the likelihood function. You can do Bayesian statistics, you can formulate marginal likelihood integrals, you can do everything we did in the discrete case. You just have to be a little bit more careful, right? So to talk about the likelihood, now you have to make statements about the density, right? So earlier we just took a monomial in the probabilities. That wouldn't quite work here, so you have to sort of take a differential formulation involving the densities. Okay? Since we only have 18 minutes, I want to spare you that and just state a proposition that talks and characterizes the maximum likelihood estimate. So let mu hat sigma hat be the maximum likelihood estimate for our data. Okay? So we're given the samples. And we want to estimate, Rainer has a model. Rainer has a set theta of covariance matrices he likes. Okay? So in his set of covariance matrices, we want to pick the one that best explains the data, that maximizes the aforementioned mysterious likelihood function, and then that point mu hat sigma hat can be calculated algebraically as follows. Mu hat is very simple. It's actually just a sample mean. Right? So since we have no constraints, the sample mean maximizes as far as the mu is concerned. The interesting part is sigma hat. So the maximum likelihood for the covariance matrix is the maximizer of the following function minus the logarithm of the determinant minus the trace S inverse S, check me Alina, times sigma inverse, the inverse of the covariance matrix, and we do this over Reiner's model. Okay. So among all covariance matrices that run for competition, we're maximizing this quantity. Okay? Let's check that this makes sense. So sigma is a positive definite matrix. So the determinant is a positive number. The logarithm of a positive number is well defined. It's a real number. It could be positive or negative, right? Minus of that is well defined. So this is a well defined function. S is a fixed matrix. That's the sample covariance matrix. That's the matrix product times sigma inverse. That's exists. It's a function on the cone, right? Because I'm only looking at positive definite matrices. And then the trace is the sum of the diagonal entries. Okay? So this here, that's a rational function in sigma. And this is not a rational function in sigma. Yet. Okay? So that's the function we want to maximize. So Rainer has a model. We want to solve this not quite yet rational function over his set. But you know, the logarithm among friends is a rational function, right? Because the derivative is 1 over x. So as soon as you write down the critical conditions, as soon as you write down the k, so if theta is given by polynomials, which it will be, then the derivatives are rational functions. If you clear denominators very, very, very gracefully and carefully, you clear denominators, and then you solve the corresponding system of equations. Okay? That's how we're going to calculate them. And we're going to give it to Matt, in Bertini, and he comes back and says sigma hat is the following n by n matrix. Okay? So let's talk about the graphical case. For every conditional independence statement, what does this mean in terms of Gaussians? Okay? Well, let's tie things together. So if we have a conditional independence statement, I is independent of j given k, what does that mean? This corresponds to a submatrix of the covariance matrix. So we take the submatrix with row indices I, what are we doing? Ij. So we take the I union k and j union k, whose rank is bounded. Is at most k, the cardinality of k. Okay? So you have a conditional independence statement. I independent of j given k. Let's look at the set I union k. You pick those rows of sigma. Then you look at j union k. You take those columns of sigma. That's a rectangular submatrix of the covariance matrix. It has more than k rows and more than k columns. And the condition is that the rank is at most k. So that's a condition. Okay? That's equivalent. So for a Gaussian distribution, if you run through the calculus, this is what conditional independence translates into. Okay? Now, in particular, if I and j are singletons, you can phrase that as follows. So condition I independent of j given k, where I and j are singletons, then this is one equation. Holds for your covariance matrix if and only if a single almost principal minor vanishes. So sigma I union j, comma j union k, I k, j k has determinant 0. Right? Because what do I mean by almost principal minors? Well, in a symmetric matrix, a principal minor you get by taking the same row indices and the same column indices, but here we differ by 1. Right? So it's not quite the principal minor, but we're off by 1. We call that an almost principal minor. So that's a k plus 1 times k plus 1 matrix, and saying that that has rank at most k just says the determinant vanishes. The inverse of the covariance matrix plays a prominent role, and this has a special name. This is called the concentration matrix. So the inverse K of the covariance matrix is called the concentration matrix. Now note that if you have a pair of matrices, one inverse to the other, that the minors of sigma and k are complementary. Yeah, everybody knows this, right? So complementary minors vanish. Yeah, so Lee, you have a 5 by 5 matrix here, and you have its inverse over there. They're both 5 by 5 matrices, right? You pick a square submatrix over here, maybe a 2 by 2 submatrix, and then you look at the corresponding 3 by 3 complementary 3 by 3 submatrix over here. They are equal up to a global constant, right? Both matrices are invertible, right? And then every 2 by 2 minor of this matrix is equal to the complementary 3 by 3 minor of that matrix, up to a global constant, which is the determinant. Okay, so remind you of that. So minors, if you have a pair of two square matrices, one the inverse to the other, then some minor of one guy vanishes if and only if the complementary minor of the other one vanishes. Now you're ready to go, right? Frank has a list of conditional independence statements. Okay, that these are things about the world he would like to find out, right? So, you know, is it going to be hot in Korea in July? You know, that's independent of something that happens elsewhere, you know, conditioned on the Middle East crisis or something, right? So then there's some other statement, and we make measurements, right? So how bad it's in the Middle East, that's a number. And the temperature on July 15th in Daejeon, that's a number, right? So we make these measurements, and now we want to estimate the covariance matrix based on these measurements. And then, you know, Frank's model translates into rank conditions, determinants of submatrices. And then, you know, here's the optimization problem that we use to solve. Let's come back and wrap this up, and let's talk about undirected graphs. What does all of this mean for Markov random fields? Now, if you have a graph, directed or undirected, we have a list of conditional independence statements. That list translates into rank conditions on the covariance matrix. Commutative algebraists call this a determinantal variety, or ladder or structure determinantal variety. So now we have this structured determinantal variety on symmetric matrices. So what are we going to do with this? So for example, for graphs, remember we have the conditions are saturated. I given j is independent of everybody else whenever there's a non-edge. For every non-edge, this statement holds. So this holds for sigma, well, if and only if the entry kappa ij is 0. Okay? Let's take a breath. Okay? So this statement translates into an almost principal, almost maximal minor of the covariance matrix. Right? So we have the n by n covariance matrix. This statement with this rule says that an n minus 1 times n minus 1 minor is 0. Right? K is everybody else, right? So the n minus 2 guys and everybody else. So this is an n minus 1 times n minus 1 minor. Well, that minor is 0 if and only if the corresponding 1 by 1 minor in the concentration matrix, the inverse, is 0. Right? So therefore, in the graphical case, for every non-edge of the graph, an entry, an off-diagonal entry in the concentration matrix is 0. Pretty simple equations. Okay? So here are 3 equivalent formulations for the MLE. Okay? So we would like to now solve an optimization problem. We, meaning us, in problem 8, under Abraham's leadership, we'll look at 4x4 positive definite matrices sigma, where the inverse has 2 zero entries given by the non-edges in the 4th cycle. And over that set, we're solving the optimization problem in this proposition. I'm going to give you 3 formulations of this that are all equivalent. You can try them all. Okay? So number 1 is the one in the proposition. So maximize, so for a Gaussian graphical model, we're maximizing log det of sigma minus the trace, log det of kappa minus the trace of S kappa over a certain set, namely the spectrahedral cone of all positive definite n by n matrices whose entries are 0 on the non-edges. Okay, this is a translation of that proposition. Okay? The determinant of a matrix is the reciprocal of the determinant of its inverse. So log det of a matrix is minus log det of the inverse. So if I replace this sigma by its inverse k, that minus goes away. Okay? This is already the k, and the minus survives. Right? So the function is written over the inverses. We're taking the log det of the concentration matrix minus the inner product of the concentration matrix with the sample covariance matrix. Right? And we're doing this over all matrices, concentration matrices that have a certain pattern of 0 entries, namely on the non-edges. That's the first version of the optimization problem. Then there's a third version and a second version. Well, the third version, let me write that as the third. So sigma hat is the analytic center. Well, let me do the second version. Let me make more space. Okay. So, blah, blah. Maybe I'll erase this. So let's have version 2 and version 3, and then time will be up. So version 2, find positive definite matrices K and sigma that are mutually inverse. Sigma times K is the identity, right? Such that kappa ij is 0 for all non-edges, and sigma ij is Sij for all edges. That's equivalent. I like formulation 2 because that's kind of a symmetric formulation, right? So that's a little bit like the complementary slackness conditions in semi-definite programming. Lee knows this very well. Everybody who does optimization knows that the complementary, the symmetric formulation using complementary slackness, that's a nice formulation. In algebraic geometry, we call that the conormal variety. Okay, so say this again. So we're now looking at an inverse pair. Sigma k is the identity. These are supposed to be positive definite. Those are the inequalities. And the concentration matrices, we are saying that the non-edges have entry 0. And on the covariance matrix, on the edges, we're putting whatever we sampled, putting this covariance samples. So that's sort of a symmetric formulation that is equivalent. And finally, the third formulation is that describes purely in terms of sigma. So sigma hat is the analytic center. By which I mean the maximizer of log det. Of the spectrahedron. That's gotten by fixing the sufficient statistics. So it's a set of all positive definite n by n matrices such that sigma ij is Sij for all edges and for the diagonal entries. I should have said that, for edges and diagonal entries. Okay? Every bounded spectrahedron has an analytic center. An analytic center is simply the place where log det is maximal. A spectrahedron, as you may recall, is a collection of positive definite n by n matrices, a linear space worth of such matrices. So that convex body, well, in the interior of this convex body, the determinant is a strictly positive number. On the boundary, it's 0. Log det is a concave. Is this concave or convex? Concave function, right? So therefore, it has unique maximum. Okay, and that's the analytic center. Linear programming, as you know, is semi-definite programming for diagonal matrices. So if we pick a diagonal matrix, we get this analytic center of a polytope. That's the analytic center. So the covariance, the MLE for the covariance matrix is either gotten by calculating the analytic center of the spectrahedron of all covariance matrices that respects the sufficient statistics coming from the sample covariance matrix, or we can do this on the other side. We can do this on the inverse, or we can choose a symmetric formulation, and you're herewith invited to try this for the 4th cycle. I'll see you at 3.
And you don't need the non-zero condition over here?
No, here I don't need the non-zero condition. So here the non-zero condition goes away. It's taken care of by the max. So here the critical condition for this maximization problem will force the inverse to have zeros in the right spot. Yeah. So here's the symmetric formulation. Doesn't look like an optimization problem, but just like in linear programming, I can either do it, optimize on one side, or I can optimize on the other side, and then the critical conditions, force the equations that we see in the middle. Okay, this was a lot of stuff, and I said this was the hard lecture, so tomorrow it's going to be easy, and this afternoon will be fun, and you'll be rewarded by a hamburger.